I'm very happy to be here. Thank you to the organizers for inviting me and all of you. I'm going to be talking about some work with my student, Umang Bhaskar, and Elliot Anchelevich, who's at Rensselaer. And this is about Stackelberg strategy for routing flows over time. Our motivation is to study what happens in traffic networks. So it could be a transportation network or a communication network, or perhaps an evacuation network. So what we're interested in is we have a model where there's a delay on the edges, and which increases with the usage of the edges. And what we're interested in, well, one thing we might be interested in, what's the optimal routing, the one that minimizes some function of the delay, and I'll be looking at several different functions in this talk. Here we don't have a choice about the optimal routing because players choose their routes independently, and their delay is going to depend on the routes other players choose. And we're interested in the equilibrium of the system, this has been studied in many contexts. And so we're going to be comparing the function of our delay for the worst equilibria to the delay of the optimal routing. This has been studied a lot in static networks, where the flow is time invariant. So it's fixed and the flow repeats over time, but it's the same flow all the time. And what we're interested in is a different model where flow takes time to travel. So we're going to have a fixed capacity on the edge and a fixed delay for the edge. And the flow on the edge may vary with time. So for example, if we might have a link that allows us 100 bits per second and has a delay of 2 seconds, and if we want to send 1,000 bits, then we'd have an arrival graph that looks something like this. Since the delay is 2 seconds, even if we start sending our flow at time 0, it doesn't arrive until time 2. And then at time 2, we get 100 bits, and then we get 100 bits for the next 10 seconds, and we are finished at time 12. Okay, so we're going to be looking a lot at these arrival graphs in this talk. Okay, so the total time takes 12 seconds. And one thing the optimal would be is the quickest flow. It's a flow that gets to the destination as quickly as possible. So in this particular example, this is the quickest flow because it's so simple. It's just one link. So what we're looking at are routing games in a flow over time setting, and so we call these temporal routing games. And the players are interested in minimizing the time they reach their destination. So we're going to make some assumptions. This is the first time this is studied, and it's typically easier to study infinitesimal players, so we'll assume our players are infinitesimal. And we're going to be looking at these arrival graphs, so the flow is going to arrive at some beginning fixed at time using some paths, and then as time progresses, more and more paths will be used. And the total area of this graph is the total amount of flow that we're trying to send. The players, we're going to assume, are ordered at the source, and each player is going to pick a path from S to T to minimize the time it arrives at the destination. So here's a very simple network that's a little bit more interesting than a single link. The capacities and demands are given for each edge. I have a fixed amount of flow. And initially, there's this delay 0 path. So the users are going to take this delay 0 path. But there's going to be more users taking this path than I can actually put on the second link in this path, because the second link only has capacity 1, whereas the first link has capacity 2. So what's going to happen is that the users coming on the first link are going to form a queue on the second link of people who want to use the second link but can't. And they prefer this link to the top link because this link, the bottom link, has delay 0, where the top link has delay 1. Okay, so over time, this queue is going to grow. Okay, we're going to assume these queues are first in, first out. And what happens over time is that this queue grows, and eventually the top link starts to look attractive because the queue on the bottom link has grown so much is that its delay formed by the queue equals the delay of the top link. So eventually users are going to start to use the top link, but the top link has delay 1, so they're not actually going to arrive at the sink yet. And finally, when they arrive at the destination, now we have traffic from 2 links arriving at the destination, so the rate of arrival at the destination jumps up, and that's reflected in the arrival rate graph on the right-hand side. Okay, any questions with that model? And so the total area is the total flow that we've sent. In contrast to this equilibrium behavior, in the optimal flow, no queues will ever form, and we'll start using all the paths that have short enough delay at the beginning, so that our arrival rate at the destination will jump up a lot earlier. They'll jump up as soon as the path that has the second largest delay starts reaching the sink. Okay, so this is and we see that the equilibrium takes more time because it took more time for the second path to start being used. In this model, equilibrium exists. This is due to work of two groups, Koch and Scutella and Comenetti, Correa, and Lahr. This is both fairly recent work. And this is for the single source, single sink case, which is the case we're analyzing. It also happens to be unique, and this is shown in the second paper. And so what we're interested in is how does the equilibria compare with the optimal, and what's the price of anarchy in this model. So as I said, there's several different measures we could be using. So one measure would be what's called the evacuation price of anarchy, which is I fix the time-bound t, and I ask how much flow can I get to the destination by time t. A second model would be the time price of anarchy, which is, in this case, I fix the amount of flow and ask how long does it take for all the flow to get to the destination. A third model would be the total delay price of anarchy, where again I fix the flow amount m, and I look at the average time it takes to destination, or the total time over all units of flow of the time it takes to get to the destination. And the final measure I could look at is the maximum delay of the player, looking at the time it takes from the time he leaves the source to the time he gets to the destination. So those are 4 different measures that I could look at for optimal and equilibrium. And there's some lower bounds on the price of anarchy in these models. So Koch and Scutella showed in the evacuation price of anarchy, there are examples that do as bad as log n. And for the time price of anarchy, there are examples that do as bad as e over e minus 1. Mako, Larson, and Steskal showed that in the maximum delay price of anarchy, there are examples that do as bad as order omega n price of anarchy. And so what I'm going to talk about in this work is that in the middle 2 models, we can get a constant price of anarchy if we reduce capacities. And so these are upper bounds on the price of anarchy in a model. Then there weren't upper bounds before. Questions? Okay. What I'm going to talk about is we're going to be able to enforce a bound on the time price of anarchy of e over e minus 1 by reducing edge capacities. And if you notice in the previous slide, this is going to be tight because we have a matching lower bound due to Koch and Scutella. And what we're going to do is we're going to compute the quickest flow, and we can do this in polynomial time due to an algorithm of Ford and Fulkerson. And then once we know what that quickest flow is, we can reduce the edge capacities so that the quickest flow saturates all the edges in the graph. Okay? And once we do that, so for example, here's a quickest flow in this graph. And if we notice that the capacity of this edge with the arrow on it is 1.5, but I'm only using it as capacity 1 in the quickest flow because the next edge in the path only has capacity 1, and so there would be no reason for me to ever want to send more than 1 unit on this arc at a time because it couldn't get to the next arc, and we don't use queues in the optimal flow. There's no need for them. So what I would do is I just reduce the capacity of that edge to 1, and the optimal flow hasn't changed because it wasn't using that capacity before. So I'll be comparing the equilibrium in this network to the optimal in the original network, and the optimal, since the optimal hasn't changed in this network. And so what we show is that if we have an example where the quickest flow saturates the graph, then the time price of anarchy is at most e minus 1 in that graph. And since the optimal hasn't changed since we changed the graph, it's at most e over e minus 1 comparing to the optimal in the original graph. That's our first result. And then we also look at the total delay price of anarchy, and we show that if again, by the same construction, reducing the capacities in the same way, we can show that the total delay price of anarchy is at most 2 over e minus 1. Okay, so this we don't know to be tight. In fact, we believe the right answer for the total delay price of anarchy matches the top, but we haven't been able to show it. I didn't look at what time I started. Jason?
So you reduce the capacities, is the price of anarchy
We don't know. So we weren't able to show a bound on the price of anarchy without doing this. So this is what we can show. That's one of the open questions. We don't have any examples where it's worse than E over E minus 1. So the Cauchy-Squatell example is the worst example we know. And it happens to be a case of this form where the optimal saturates the graph. We'd like to be able to prove that that's the worst case, but we haven't been able to do that. Yes? All the graphs we're talking about are capacitated. It's just a question, what are the capacities? So I'm measuring the ratio of the equilibrium in the revised graph. There's a unique equilibrium in the revised graph to the optimal in the original graph, okay, which is also the optimal in the new graph. So you could pick your worst case optimal, it's the same, or your best case optimal. Sorry. Yeah. Thank you. So I'll talk about, I won't be able to give you much of the proof, but I'll try to give you some ideas. I'll talk about the structure of the quickest flow, the structure of Equilibria, and I'll sketch a much weaker version of our main theorem. So a quickest flow is a static flow repeated over time. So it consists of flow, it's basically a flow of value 1 on the top path, a flow of value 1 on the bottom path, starting from time 0 and ending at a time where it's the last time it'll be able to reach the sink. And so we get an arrival graph that is at rate 1 until the second path reaches a sink, and then it jumps up to rate 2. In Equilibria, we don't start using all the paths at the same time. We start using the shortest path, the least delay path, until the queue grows large enough, and then we start using another path, etc. Okay? And so Equilibria proceeds in these phases, and a phase is characterized by the set of edges used and the set of edges with queues. So within a phase, the flow rate is fixed. It's determined completely by the paths that we're using. And what happens over time is that we either add edges to the graph or queues might drain, in which case the number of queues reduce, and then new queues might start. So what I'm going to be able to talk to you about in this talk is I'm going to make an assumption about the number of phases. I'm going to talk about a one-phase equilibrium, so a particular example that happens to have an equilibrium that completes in just one phase. And I'll show you that the time price of anarchy is at most 2. So it's a little bit worse than our main theorem. So I need to do this, I need to get bounds on the equilibrium. And I'll do this, I'll get a couple different bounds and compare them. So what we're looking at here is we have a total amount of flow. This is a one-phase equilibrium, so the flow rate during a phase is fixed, and all the flow is going to complete by just using one set of paths. So our flow arrival graph on the right is just going to have a constant arrival rate until it completes. Okay, and the arrival rate we're going to denote as CE. In optimal, we're not imposing any constraints on optimal, and so optimal is going to start using all the paths, and the maximum capacity used by optimal we're going to denote as maximum flow rate is C0, and it could jump up and it'll complete before equilibrium. The area of both graphs, since they're both sending the same amount of flow, the area under the curve in both graphs has to be the same. So because of this observation that the area under the curves have to be the same, the area for equilibrium is CE times equilibrium. The area for opt is, well, it's at most C0 times opt, because that's an upper bound, because opt can jump up. And so we get the first bound on equilibrium, that CE times equilibrium is at most CO times opt. So equilibrium is at most CO over CE times opt. A second bound on equilibrium is going to come from using this notation tau of theta. Tau of theta is the minimum time it takes to reach the destination at time theta. So this is going to be increasing function of theta, because as time goes on, queues are getting larger and larger. So the time it takes starting from the source to reach the destination increases. So our second claim, which I'm not going to prove for you because it's a little bit complicated, is that we can bound this from below by C0 minus CE over C0 times equilibrium. And let's just take a quick look at this and think about why this is true. So if the CE is much less than CO, that means that the equilibrium is using very little of the true capacity of the graph. which means that the queues are growing because we're using very little capacity, so it means a lot of flow has to get held up in queues. So there's going to be a lot of delay due to queues, and therefore our delay as a function of time is going to be increasing a lot, so that the bound is going to be larger. Whereas if equilibrium is using a lot of the capacity of the graph, then the delay on any edge is going to be a lot smaller because our delays are due to queues. Okay, so now let's use this claim. So this claim says something about what's happening over time as equilibrium proceeds. So we know that if equilibrium is not using the full capacity of opt, in which case it's not opt, there's a path in the graph of length at most opt not being used because opt uses that path. And so, but if that path is going to start being used by equilibrium when the delay equals the delay on that path. So when tau of equilibrium, when tau of theta gets bigger than opt, this path should be used, which means that we have a change in phase. So we have another phase. And since we're under the assumption that we have a one-phase equilibrium, this won't happen. Equilibrium will end before this point. Okay? So that gives us the second bound that tau of equilibrium is at most opt. Because if tau theta gets above opt, the phase ends and we have a new phase. So I put those two together and solve for equilibrium, and we get this bound on equilibrium. Equilibrium is at most C0 over C0 minus CE of opt. So we have now two bounds on equilibrium. We can try to maximize this by choice of CE. If we pick CE equals C over 2, then we get the equilibriums at most twice opt. Okay? So that's a proof in a very simple case. So for a one-phase equilibrium, the time price of anarchy is at most 2. Just in case you're interested, all these lower bounds are all one-phase examples. So the worst cases we have are all one-phase examples. So just to remind you, what we prove in general is a better bound, E over E minus 1, and we prove it for arbitrary number of phases. And for a total delay, we also get to E over E minus 1. And these imply that we can enforce these bounds. The proof is available in our paper, which is on my website. So there's some open questions. So the first question was raised earlier. What if we don't restrict the capacities? If we don't change the capacities at all, does the price of anarchy actually exceed E over E minus 1? We don't have any examples to suggest it does. We looked at the single source, single sink case. You could also ask the question, what's the price of anarchy for multiple sources? As a starter for this question, you might want to understand what's the structure of equilibria for multiple sources and when do equilibria exist, and we don't know the answers to that yet. And another interesting question is what if players have imperfect information? So involved in this is under the assumption of this model, players can know what the best path for them is, and already we're not even sure how to do that exactly in polynomial time. So if they don't know how to find the best path, what if they choose something that's not quite the best path? What is equilibrium in that model? Thanks for your attention. Tim.
I've looked at the question of how much capacity reduction can improve equilibria in the spirit of Price's paradox type question.
So I don't know what the price of anarchy is in the model without capacity reduction. So it partially.
Forget about opt. Just say you have a network, you have equilibrium, let's reduce capacity, make the equilibrium as much possible. And the question is how much faster you'll get capacity reduction.
I don't know. There was another hand up?